Hi everyone. So today let us discuss about non-aqueous titrations. Okay, non-aqueous titrations. First of all, by the name itself, non-aqueous means titrations which does not involve water. Aqueous, we know that it is nothing but water. So how you're going to perform them? We would be taking solvents. Usually, titration we will be taking either any acidometry or alkametry. If you take, what happen, we will be having a titrant or titrate. Two will be there. In that, we will be doing the titration by adding indicator and we'll get endpoint. That is what happened. So here, non-aqueous titration means when you're titrating those solutions which does not have water, we will be using solvents other than water. So here, why we need to go towards this non-aqueous titration? Usually what happens means when we try to titrate such compounds which are having a mixture, like for example, mixture of acid or base. Okay, so in that it would be difficult to perform when they are dissolved in water. And strong acid, weak basic mixtures that are impossible to get the endpoint with the simple aqueous titrations. And it is impossible to separate the mix of acid bases with near constant of dissociation, because usually in acidometry, alkalimetry, we have a certain endpoint between acid and base. Okay, so here another thing is that there are certain compounds, usually if you take organic compounds, which would be insoluble in water. So we need to assay, like for example, if you want to perform an assay for paracetamol or any of the drug, and let us suppose it is not dissolved in water. So how can you assay, how can you identify if it is not dissolving? It is not dissolving, and how can you get the point results? So for that reason, so such compounds which are insoluble in water, as well as such compounds which are having a mixture of acid base, okay, and which are having weak acid, weak base, they cannot be titrated by normal acidometry, alkalimetry, by aqueous titration. We need to use different type of solvents which are other than water. So such type of titrations are regarded as non-aqueous titrations. So here, first of all, let us see a few of advantages, like why we are using this non-aqueous and where they are applicable. First of all, organic acid and bases that are insoluble in water, we can soluble them in non-aqueous solvent and we can perform a titration. Next, non-aqueous solvent may be help to or more acids mixture that can be dissolved, and the individual acid can give separate endpoint in different solvent. And next, enlargement of solubility range. It can enlarge the solubility range, like we can take fats, oils, which are not soluble in water, that can be titrated or that can be dissolved and titrated by non-aqueous titrations. And applicational range, it is enlarging. Like we have a certain limits where aqueous titration are unable to perform, give the endpoint. So elaborating that limits, we can go with the non-aqueous titration, like weak acids, weak base, then we can titrate them with non-aqueous solvent and we can perform the titrations. Next, substance or compositions that cannot be separately determined. That would be usually mixture of compounds are there, mixture of acid and base is there, and it cannot be easily determined by acid-base titration. Then we need to go towards non-aqueous. And as we have seen, like weakly acidic, weakly basic, and non-aqueous titration are simple, accurate example of non-aqueous. It has been given few examples. Ephedrine preparation is being assayed by non-aqueous titration. Codeine phosphate, okay, and tetracycline, tetramycin, and antihistamines, various piperazine preparations that would be done with the non-aqueous titrations. So, okay, for we are telling non-aqueous, non-aqueous. What is non-aqueous here? Actually, we are taking the solvent, the compound in which we are going to dissolve that solvent, we are using it non-aqueous. So here, the non-aqueous solvent we are using, again, it would be of different types. What are the various types of non-aqueous solvents that are seen in non-aqueous titrations are? First is aprotic, second one protogenic, third one is protophilic, and fourth one is amphiprotic solvents. So here, usually these solvents, what we are doing, taking, they are responsible for leveling effect. Hence, this weak acid, weak bases, they need to level up to give a proper result. So based on to level them up, we would be using this non-aqueous solvents. So here, if you go towards aprotic solvents, they are not at all having any sort of reactivity. They are mostly inert and they work as a catalyst. Okay, non-protic, that is not having any sort of sharing ability of proton and all. So they are called as non-aprotic solvents, which does not have any sharing. So they does not show leveling effect, aprotic. Remember that they does not show leveling effect, but still they are helping converting the reaction or helping the reaction to occur fast. So they increase the rate of reaction. They are neither acidic nor basic, that is inert solvent, but still they act like a catalyst and help the reaction or getting the endpoint faster. Example, chloroform and benzene are aprotic solvents which does not react, does not have acidic or basic nature, but still increases the rate of reaction. This means they does not show leveling effect, but still help the reaction to proceed faster. Next, protogenic means which are having protons in them and they are acidic in nature. They can donate proton and they have the strength of enhance the strength of weak bases. Like if you're taking a weak base, then it is better to use a protogenic solvent because it will help to level that up. Leveling effect will be there here. So protogenic solvents are much better used for the weak bases. Example HCl as well as H2SO4. These are example for protogenic solvents. Next, protophilic, the one which loves proton because they are basic in nature. Means they would be accepting the protons. So basic in nature, they will be also showing the leveling effect, but they accept the proton. So it is like opposite to that of protogenic. Okay, so they are protophilic. They have which have high affinity towards the proton. Example, liquid ammonia, amines, and ketones that will act like a protophilic solvent. So here which means that they can be helpful for uh, leveling up weak acids that will be there. So that will be leveled up by this protophilic solvents. Next, amphiprotic solvent. Amphiprotic means by the name itself, it is having the amphibians. I think for example, I'm giving like amphibians means what? The one which lives both in water as well as land. Means which is having both the features. We call them as amphi. So here amphiprotic, which means that it is having both protogenic as well as protophilic property based on what it is there available. Based on that, it can have the ability to change its nature. So that is there in water itself, but we are concerned with non-aqueous. So we will consider alcohol and weak organic solvents as our non-aqueous amphiprotic solvents. So here they would be having both acidic and basic in nature. Based on what is being required, they will show their effects. So such type of solvents are called as amphiprotic solvents. So how we are going to detect the endpoint? So visual indicators are formed to a suitable, most suitable for the detection of endpoint. So the important indicators used for non-aqueous are crystal violet. It is will be used as a 0.5 solution in glacial acetic acid, and it will give violet color in basic medium and yellowish green in acidic medium. Okay, and it is most widely used for the titration of pyridine and perchloric acid. Even thymol blue will also be there. It is not mentioned here, thymol blue. This thymol blue will be having a red color in acidic medium and yellow color in the basic medium. If you take thymol blue, okay, then we have oracid blue B indicator. It is also being used in the form of 0.5% glacial static preparation, and it gives by the name itself blue color in basic medium, while pink color in acidic medium. So now selection of the solvent. How you are going to select the non-aqueous solvent. So acetic acid used for titration of weak bases. Nitrogen containing compounds we will be using acetonitrile or acetic acid, metal ethanoids will be used, alcohols or non-basic alcohols like that will be there. So soaps and salt of organic acids. Okay, dimethyl formamide. In that we will be using benzoic acid and amides. Okay, alcohols in that N-butanol. NBA is nothing but N-butanol will be there, and IPA is that isopropyl alcohol. IPA, which has been mentioned. So this isopropyl alcohol and N-butanol that would be used for soap and salts of organic acid. Dimethyl formamide, it is used for benzoic acid and amides. Okay, so these are certain list of solvents that would be commonly used. And coming to perchloric acid in acetic acid, so that is used for the detection of amines, amine salts, amino acids, and salts of acid. If you are taking any of this category, like either amine salt, amino acids, or salts of acid, it's better to use perchloric acid in acetic acid as our non-aqueous solvent. Next, sodium methoxide in toluene methanol is being used, and quaternary ammonium hydroxide in acetonitrile pyridine. It has been used for acids, enols, imides, and sulfonamides. So if your compound belongs to any of this category, then quaternary ammonium hydroxide, which is dissolved in acetonitrile and pyridine solution, that would be used as a solvent. So now, assay of non-aqueous titration. So here in that we have again like how we have acidimetry and alkalimetry in aqueous titrations. A similar way in this also we will be having. So it can be further divided into this acidimetry, to be specific, if we take like based on titrant. If when you're titrating with acid, we call it as acidimetry. When you're titrating, like when you're burette, if you take alkali, we call it as alkalimetry. So here titration of primary, secondary, and tertiary amines that can be done by this acidimetry. And alkalimetry, in that we will be using non-aqueous titrations, like titration of acidic substance, because alkali is going to take as titrant. So for acidic substances, we will be using alkalimetry. So here it has given certain 4 steps, what we need to see here. So look here, temperature maintenance is quite important. Like that could also affect our what do you say, reaction and all non-aqueous reaction. So here methodology which will involve for primary amines we are taking. So primary amines that can be done the standardization with the help of perchloric acid as non-aqueous solvent. Okay, so here titrant we are going to use. So here whenever you're going to use a titrant, we need to perform a standardization on it first. So preparation of zero point 0.1 normal perchloric acid. Then we need to use the standardization method to standardize perchloric acid. Then selection of indicator. Okay, so whatever the indicator it has been suitable for such compounds, we would be taking the such type of indicators. So here effect of temperature on assays that we need to check. So now we are taking an example here. We are preparing 0.1 normal perchloric acid. How we are going to prepare? So for preparing this, we need to take 88.5 ml of perchloric acid, and perchloric acid will be coming in various percentages. So here we are taking 70 to 72%. That sort of perchloric acid we need to take 1 liter of glacial acetic acid and 30 ml of acetic anhydride. So how we are going to use prepare? Gradually mix 8.5 ml to 900 ml of glacial acetic acid, vigorously continuously stirring. Then we need to add 30 ml acetic anhydride. Then level up the volume to 1 liter with glacial acetic acid. So after preparing, we need to make it to stand for 24 hours, because at that moment itself, all will not uniformly mix. It will take a time. So in order to become a proper 1 normal perchloric acid solution, it will require a day time. So we need to, if you are going to perform test tomorrow, like assay you're going to perform using perchloric acid tomorrow, or like day after tomorrow, better you prepare a day itself, because one day you need to keep 24 hours. So like 2 days before itself, you need to have this preparation prepared. Then after a 24 hours gap, you can use it. So acetic anhydride reacts with water So in perchloric acid and some traces of glacial ice, they make the resulting mixture practically anhydrous. So when they will be like whatever the water and all will be there left out, that will be also absorbed and make it anhydrous, means does not having any water. So you'll be having acetic anhydride and making it fully acetic acid. So now standardization of perchloric acid. For standardization of perchloric acid, potassium hydrogen thalate is being used. How you're going to standardize? We are going to standardize by taking potassium hydrogen thalate. And here, weigh accurately 0.5 grams of potassium hydrogen thalate in 100 ml conical flask, then add 25 ml of glacial acetic acid and attach a reflux condenser, then warm up the solution mixture until the salt get dissolved completely, whatever the salt we have added, and cool and titrate with 0.1 normal perchloric acid. Make the use of either of two, like either you can take Oracid blue 2 drops or crystal violet 2 drops. Endpoint will be blue to blue green. And for Oracid blue, you would be having blue to pink color. So any one you can take and you can standardize the perchloric acid. Now, choice of indicators, okay, when you're going to use. If you can just see here, quinaldin red, it will be having this magenta color in basic medium. And in neutral, it won't show any such change. But in acidic medium, it will be almost colorless. Okay. And naphthol benzene, 0.2% in glacial acetic acid, it will show blue color in basic. In neutral, it is orange. And in acidic, it will be giving dark green. Because this non-aqueous indicators, they would be giving some usually like for quinalidin red, it would be giving only two changes, two color differences, but usually they would be having three changes. Like in neutral, there will be different color. In basic, there would be different color, and acidic, there would be different. Like for example, Olarset blue B, it would be giving basic. It will be showing blue color. In neutral, it is purple, and in acidic, it would be pink. Okay, so crystal violet, it would be in the name itself basic violet, and neutral bluish green, and acidic yellowish green. Okay, thymol blue is also there, which would be yellow in basic, and red will be there in the acidic medium. Perchloric acid precautions is usually available in 70 to 72 mixture with water. So that is the reason we need to keep it for 24 hours. So whatever that 30% water is there, it needs to get absorbed. So for that reason, we would be keeping. So usually undergo spontaneous explosive decomposition. Therefore, it's available always in the form of solution. So that is why it need to be kept in the solution itself. Conversion of acetic anhydride to acetic acid requires 40 to 45 minutes. So it's being an exothermic, solution must be allowed to cool at room temperature before adding glacial acetic acid. So it requires that 40 to 45 minutes. And in that time, it might explode. Okay, so that is why it needs to be kept at cooling or lower temperatures. Next is avoid adding excess of acetic anhydride, especially when primary and secondary amides to be acid. Why? Because they would rapidly convert to their corresponding acetylated non-basic product. So here um, we need to be like add excess of acetic anhydride should not be added because that could lead into acetylated product. So in order to that limit which is there, that much amount only have to be added. And perchloric acid is not only a powerful oxidizing agent, but also a strong acid. So because it is a very strong acid, so we need to take a proper care while handling it because spilling on the hands and all, it could be very harmful. Next, other examples, how what sort of indicators that could be employed by the various substances. Like amantadine hydrochloride, will be employing crystal violet as indicator. And for chlorpromazine hydrochloride, methyl orange is being used. Clonidine hydrochloride, alpha naphthol benzene has been used. And cryoheptadine HCl hydrochloride will be using crystal violet. And for ephedrine hydrochloride also, crystal violet is being used. Now we are preparing 0.1 normal of potassium methoxide in toluene methanol solution. So here we need to take absolute methanol 40 ml, dry toluene 50 ml, and potassium metal 4 grams. So first of all, into a dry flask, means which is not having any water, such sort of flask we need to take, add a mixture of 40 ml methanol and 50 ml. Dry toluene also, it means that toluene which is not having any amount of water in it. So cover it loosely, carefully add freshly cut pieces of potassium metal. Okay. So here what happened, above mixture will constantly shaking. So whole dissolution of potassium metal occurs. So add enough absolute methanol to eat clear solution. So again, toluene 50 ml is added with constant shaking until the mixture turns having a hazy appearance will occur. So till then we need to add. The process is repeated by alternate addition of methanol and benzene until 1 liter. Okay, so methanol and toluene, sorry. So that would be done like 40 ml methanol, 50 ml toluene. In that way, we need to add to make it at 1 ml. Okay, so taking care to add a minimum volume of methanol to give a visible clear solution that you need to take. So in this way, we will be taking and preparing this 0.1 normal potassium methoxide in toluene methanol solution. So next is a potassium preparation of 0.1 normal sodium methoxide. In that way, we need to take similar manner how we have been performed for potassium methoxide. So in that way, same way we need to take, but here we need to take instead of potassium, we need to take a freshly cut sodium, 2.3 grams. And one again, if you compare with potassium and sodium will react very vigorously with the water. It will again blast with water. Okay, so even a little amount of water will be there. It will be quite hazardous. So we need to take a proper care. Okay. Next, preparation of 0.1 normal lithium methoxide, how you're going to take. So in this, we need to take 0.7 grams of lithium in place of sodium. In similar way, we'll be to make a solution with toluene and methanol. Next, standardization of 0.1 normal methoxide solution. So material required, how we are going to this sodium methoxide, lithium methoxide, potassium methoxide, whatever the methoxide you are using as a solvent or titrant, how we are going to standardize. So for that, we would be taking dimethyl formamide 10 ml, thymol blue, that has been taken as 0.3% in methanol solution, and 0.1 normal lithium methoxide. We are taking example for lithium methoxide in toluene methanol, and benzoic acid 0.6 grams. So procedure is like to transfer 10 ml of DMF in conical flask and then add 2 to 4 drops of thymol blue. Okay. And then first neutralize the acidic impurities in DMF and by titrating 0.1 normal lithium methoxide in toluene methanol, and then quickly introduce 0.06 grams of benzoic acid and titrate immediately with methoxide in toluene methanol. So we need to titrate. Care should be taken to avoid contamination with neutralized liquid or atmospheric carbon. So what is happening here is sodium or lithium methoxide will be reacting with methanol and forming sodium methanoate. Okay, so interaction of sodium metal with methanol is an exothermic. So hence special care must be taken while adding the metal. Okay, so like we have seen earlier in which we are adding the metal. So we should take a special care because it is exothermic and even it could have a minor blast in the lab if you are not going to take care that it should not have any amount of water in it. And next, the preparation of another solvent that is 0.1 N tetrabutyl ammonium hydroxide. So in this benzoic acid, 60 mg, dimethyl bromide, 10 ml, and thymol blue solution will be taken. That would be 0.3 weight by volume in methanol and 0.1 N tetrabutyl ammonium hydroxide. So first we need to take 10 milligram of benzoic acid And in that, we need to dissolve 10 ml of previously neutralized dimethyl formamide. And then we need to add 2 to 3 drops of high mol blue. Okay, so by titrating against zero point 0.1 normal tetrabutyl ammonium hydroxide. So allow the benzoic acid to first dissolve completely, then we need to titrate. So we will be getting this 0.01221 grams of tetrabutyl ammonium, uh, sorry, benzoic acid is equivalent to 1 ml of 0.1 normal tetrabutyl ammonium hydroxide. So let us summarize these all concepts fully. So here we have seen about non-aqueous titration. So let us again, I'm just giving a gist as well as few more important points we will get to know in this whole summarization part. So here, first of all, by the name itself, these non-aqueous titration are type of titration in which substance are dissolved in non-aqueous solvent. Next, this titration is suitable for vast variety of organic compounds which are insoluble in aqueous solvents. Next, this method of titration is useful for analysis of weakly basic or weakly acidic substances. What are the properties of this non-aqueous solvents? What we are going to employ. So here, first they have self-dissociation will be there. Solvents like ethanol, acetone, acetic acid, etc. are easily dissociate into components. And other hand, non-dissociating solvents like ether, chloroform, etc. do not dissociate. Dielectric constant, non-aqueous solvents such as ethanol, methanol, acetone, etc. They will have high dielectric constant, which means that they would be easily dissociate into ions without using much energy. They require very less energy for dissociation. Next, acid basic properties, like we have seen that amphiprotic, they will be having both aqueous acidic and basic, and they can solubilize and they can able to uh, identify or standardize both acidic and basic substances. Coming to first category of the solvent, aprotic. First of all, they are inert. They are not showing any leveling effect, have low dielectric constant, neutral, non-reactive, but still they will be acting like a catalyst and increase the rate of reaction. Example for aprotic are benzene, chloroform. Protogenic, which are acidic in nature, having exert a leveling effect on bases, have high dielectric constant. Example is sulfuric acid. Now, protophilic, basic in nature, leveling effect for acids, high dielectric constant, and react with acid to form solvated protons. Example, pyridine and DMF have both protogenic, protophilic properties, dissociate to lesser extent, have low dielectric constant. Acetic acid and ethanol means all three will be having a good leveling effect, but protogenic will have leveling effect on bases. Protophilic will have a leveling effect on acids. Amphiprotic, they will level both acid and bases. So what is the leveling, like phenomena of leveling and differentiating effect? So usually we will be having a mixture of either weak base dissolving weak acid, gives a base does not accept proton. When you take a weak acid, a weak base which is dissolving weak acid, that base which is won't accept proton easily. So we need to level up with using a strong acid. Okay, so the strong acid exerts leveling effect on base. Similarly, if we take a weak acid, dissolving weak base, the acid which has been formed now, which not accept protons easily. So for that, we need to take a strong base, which exert leveling effect on the acid. So that is why the selection is important. And that is why they are not giving a correct results with the aqueous. So for that, that is the reason we would be going towards this method, non-aqueous titration, where we are going to titrate with non-aqueous solvents or titrants. So titrants use for our non-aqueous titration, we can use perchloric acid in 0.1 molar glycolic acid, or perchloric acid in 0.1 molar dioxane, halogen salts of bases like HCl or NaCl, like HF, hydrogen fluoride, like that, that can be used. Lithium methoxide 0.1 molar, sodium methoxide 0.1 molar. These are various non-aqueous titrants which are used. Indicators like thymol blue, which I have seen told like in many standardization, thymol blue has came having yellow color in basic media and red color in acidic media. Okay, crystal violet, which is yellowish in acidic, and basic it will be violet, neutral blue green, quinidine red, colorless in acidic media, and magenta color will be shown in basic media. Neutral, it doesn't show any color. And oracid blue, be pinkish red in acidic media. In base, you will be having blue and neutral purple color. So what are the various official drugs that are being assayed by non-aqueous titrations? That includes nicotinamide, okay, that is being assayed by glacial acetic acid and acetic anhydride using crystal violet as indicator. Metronidazole, it will be taking a medium glacial acetic acid, and it is being used, the indicator will be like a brilliant green. Levodopa, glacial acetic acid, in that we'll be using crystal violet. Okay, phenobarbital, it will be using in the medium asperidine, again crystal violet. For phenytoin methanol as a medium, again crystal violet, and acetazolamide, dimethyl formamide, and in that also will be applying the crystal violet. So like there are various, apart from these, there are lists of drugs that would be being used for that. Okay, so that's about this non-aqueous titration. Okay, so I'll just have a, again, I'll just go through all the things for your briefing on that what are these non-aqueous titrations. Okay, so I'm just again, I'll just give an idea about it. Okay, first of all, by the name itself, we need to know that non-aqueous titrations, these are the titrations which will be employing the solvents other than water. Okay, and basically, majorly, the reason behind them is there are certain conditions in which aqueous titrations does not give a proper results. We need to go towards the a different method, because for example, like for a weak mixture of weak acid, weak bases will not give a proper endpoints and results. For that, we need to go towards a leveling effect. Means leveling effect, just now I have explained. So what is that? That leveling effect will help us. Like here it is there. I'll just explain this leveling effect, because this is the reason behind for selecting this non-aqueous titration, like phenomena of leveling and differentiating effect. So the major reason why we are applying this non-aqueous titration is weak base, when they are dissolving weak acids, like when we, in order to dissolve, in order to say, we get a base which not going to accept. Usually base accepts proton, but weak base, when it is dissolved in weak acid, gives a proton which does not give a base which does not accept proton. So we need to increase the uh, strength or level of that. Okay, so for that, weak acids exerts a differentiating effect on the base when we are uh, doing it. Okay, and weak base will be giving a leveling effect on this acids. Okay, so similarly, if you go towards strong base dissolving strong acid, okay, so when we are taking strong base strong acids, it would be leveling it up. Okay, strong acids exerts a leveling effect on base. Similarly, strong base exerts leveling effect on the acid. So this is the reason for leveling this. Okay, so when you're getting a mixture of weak acid, weak bases, we need to level that up. For that reason, we would be adding up these sort of like again based on what compound we are doing. Just we have seen there is a list of compounds for which we would be having a certain type of solvents that are being employed. Okay, so what is the reason behind them is like for leveling effect, we are using certain type of solvents. Okay, so like for non-aqueous titration, for perchloric acid and acetic acid, being acid, it is being used for the bases. Okay, like amines, amine salts, amino acids, salts of acids. Okay, potassium methoxide in toluene methanol, it has been used. Okay, quaternary ammonium hydroxide, that is being used because it is a basic. You can by see quaternary ammonium hydroxide and acetonitrile pyridine. It is basic in nature. It is used for leveling effect for acids, enols, imides, sulfonamides. Okay, so that is the reason we will be using this non-aqueous titration. We have a certain list of compounds which would be used for, excuse me, which would be used for specific uh, list sort of compounds. Okay, like we have given like acetic acid used for titration of weak bases, 9 nitrogen compounds, acetonitrile and acetic acid, methyl and metal ethanoids, alcohol, isopropyl alcohol, and butanol. Okay, so that is used for soap and salt of organic acids. Dimethyl formamide, it has been used for benzoic acid as well as amides. Okay, an important thing in this is about the various solvents which we are using in non-aqueous titration. We are using 4 different types of solvents: aprotic solvent, protogenic solvent, protophilic, as well as amphiprotic solvent. So here, aprotic solvents that would be having catalyst-like property. It is like inert, doesn't give any leveling effect of acid base and all, and it would be having just a catalyst-like property. Aprotic, which is not going to give any sort of proton and all. So chloroform and benzene. Likewise, we have protogenic. Okay, so protogenic will be uh, the one which is having acidic in nature, and they can donate the proton and enhance the strength of weak bases. Example for protogenic are HCl and H2SO4, and protophilic, basic in nature, have a good affinity, show the leveling effect for the uh, which have high process affinity for proton. So they'll be using a leveling effect for the acids. Okay, examples like liquid ammonia, amines, and ketones, they would be used as protophilic solvent for various acids. Protogenic, protophilic. Then we have amphiprotic, that will be accepting both water, proton as well as donate the proton. So alcohols and weak organic acids have this amphiprotic property. And apart from this, we have a certain major advantages, like example for non-aqueous titrants. You can just see like we have perchloric acid and etc. Different sodium methoxide, okay, and potassium methoxide. Likewise, we are having list of examples. And an important concept which is responsible or which would be affecting this non-aqueous titration is the temperature. Okay, because the effect of temperature is more for this non-aqueous titration, because when we are using these non-aqueous solvents and all, we need to see like whether the procedure requires heating or not. Because when we go towards non-aqueous like solvents and all, they are mostly like few of them are volatile. They'll get escape out and all. So we need to look into the temperature requirements, and those things plays a vital role in this non-aqueous titrations. So we got a list of various non-aqueous substances which are being titrated by this non-aqueous method. In that, we have a certain important compounds: amantadine hydrochloride, chlorpromazine hydrochloride, clonidine hydrochloride, and triphoheptadine. In that, crystal violet has been used. Clonidine, we are using alpha naphthol benzene, okay, and ephedrine hydrochloride. In that also we'll be using crystal violet as the indicator, okay. And next, we would be having various methods of preparation of various solvents. We have seen like how they have been prepared. Okay, so that is about this whole non-aqueous titrations. Okay, so which are very important in our chemistry. Okay, or analysis of various compounds. Assay of various compounds can be done by this non-aqueous titration method, in which we would be having a solvent which is not water, other than water. Why? Because there are certain limitations of aqueous titration. We need to apply this non-aqueous method. And for that reason, we have a special type of indicators which are having a specific color changes. And based on what we are titrating, the indicators vary. Okay. So, all right. That's it regarding this non-aqueous titrations. Any doubts regarding this non-aqueous titration? You can let me know. No doubts? Okay, shall we proceed with the ending of session? Any doubts?